I'm juggling an enormous number of simultaneous things.
Yeah.
Right after this, I'm going to go talk about the first.
It's like reading recording, right? Like,
Right.
they don't.
True. Okay. All right. Hi, everybody. It's making me log in. I don't know why. Oh. Hello. Okay. Let's talk about binary search trees again. We are back in an era of more aggressive immigration enforcement. Here's a tweet from 2017 where a traveler was asked to balance a binary search tree at the airport. So if you are here on a visa from another country, today's lecture may be particularly relevant. All right. At some point when you're coming back into the country. So I'm going to start by wrapping up what we did last time and talk about B trees and just summarize the best and worst case for the B tree. Here I'm showing the example where L is 2. That means you can have at most 2 things in each node. There's some annoying terminology with B trees that if you have 1 item, you're called a 2 node because you have 2 children. If you have 2 items, you're called a 3 node because you have 3 children. Lecture has started, by the way. The best case height you could ever have is if all of your tree is 3 nodes. That would be this bottom case. And it's the best in the sense that, hey, I have 26 items and there's only height 2. The worst case for a B tree is that all of the items are, or all the nodes are 2 nodes. Okay. Now, if you'll notice, both of these still have logarithmic relationship between their height and their number of nodes. This one's log base 3. This one's log base 2. So if the best case is log and the worst case is log, it's all log. If we think about the runtime for contains, the basic idea is that we need to look at each level, like 1 item in each level. The overall runtime is just going to be HL. Since L is a constant, we don't have to worry about that. And so the overall runtime is OH. What's the height in terms of N? Log N, right? So H is log N, so the overall runtime is big O of log. I use big O here. Could it be faster? Sure. So imagine you're doing a series of contains operations that's always looking for the item in the root. Those will all be constant time. I'm using O there to indicate the worst case is log N, but could be faster. Add is very, very similar. I'm not even going to say it out loud. The worst case is you have to do 1 split operation per level. Okay. But the bottom line is that both of them are log N. Okay. That's the summary of what we had last time. Here's the longer summary. I'm not going to read this out loud, but if you could read this slide later and all of it makes sense, then you've digested most of what B trees are all about. Okay, so that's where we left off last time. We had this clever tree structure where you're always between these 2 different cases, but the bad news is that actually implementing this is annoying. Okay, so the bad news is if we have a small L, I mean, we really do implement B trees. If you take a databases class, there are B trees involved, but it's not as nice of a data structure as you might like. So the BST that you implement in lab in this class, if you were to try and do a B tree, you'd find it's much more annoying. One piece of fantasy code for a 2-3 tree, so that's where L is 3, it would look something like this. You'd have to say, okay, if it's a 2-node, I'll make a 3-node. If it's a 3-node, I'll make a 4-node. If I have a 4-node, I need to split. It would be a mess. You'd have a lot of special cases. That's all I really want you to get out of this. There's an old Donald Knuth quote that beautiful algorithms are, unfortunately, not always the most useful. Okay. So I'm going to take a totally huge pivot here, and we'll come back to B trees later, much later. But first, I'm going to talk about something called tree rotation, which is a way to take our ordinary, normal binary search tree and make them more balanced. It's a way to do it. So let's imagine we have a binary search tree that has 1 and 2 and 3 in it. You can work out all the possibilities of inserts, and you can say there's 5 different possible binary search trees. Here they are. And what determines which one you get? The order you insert them, right? Now, more generally, there's going to be a Catalan number of n different BSTs. You can click here if you want to know what that is. And it turns out that there's this nice operation called rotation that will allow you to go from any of these trees to any other. Like a Rubik's Cube, there's a sequence of operations that will take you from some set of states to other sets of states. And in the case of the binary search tree, all of the states are accessible using this rotation. In general, you can go from any configuration to any other in a linear number of rotations, the specific number. Here's a paper if you want to read it. And here's a blog post. And so I'm going to tell you what rotation is, because one natural tool is, let's say I have this tree, which is not optimal. We know there's some way to rotate it into this tree, which is nicer. So let's learn what a rotation is first. I'm going to give you an example, which is I have here a binary search tree. When you call rotate, I'm going to have 2 operations, rotate left and rotate right. And both of them are going to take a specific node and transform the tree in some way. So this is one way to think about rotate left of G. So what I'll say is, suppose if X is the right child of G, the process of rotating G to the left is to make G into the new left child of X. So whoever G's right child was, now G is going to be that item's left child. And this is important, like this specific structure, this is going to preserve the search tree property. There's no change. It doesn't mess up the fact that on the left is things that are left and on the right is things that are right. And so the basic cartoon I have here is that G says, I'm going left. Okay. And this right here, that's X. So X is going to be G's new boss. In this case, X is P. Okay, so we're going to try and perform this operation intuitively. And I'm going to do it this way. I'm going to take P and make it G's new boss. So naively, I might do this. So all I did is I took P and I brought it up. And now I have G is now to the left of P. But this is a weird structure. Why? Like P has 3 children and it's only 1 item. So that's not allowed in a normal binary search tree. So I need to deal with K. K does not make sense. So where should K go? Or actually all K in its sub pieces. What do you think? Where's a safe place to put this? To the right of G. All right, so I'm going to take this and move it to the right of G. So I got transferred from P to G. And that's okay because P, now this stuff right here was all less than P. And so it's all going to be, sorry, it was all before. It was all less than P and greater than G. So when we finish that whole operation, it's still less than P and greater than G. Okay, that's rotation. Now, rotation is one of those funny things. Like when you first see it, you see this demo and you're like, great. But then if I had you try to do it right now, you'd get a little confused, and I will let you do it in a minute. It just comes with practice. You have to do like 5 of them, and then it sticks in your brain. But at first, it's a little confusing. Okay. So this is the whole summary of everything that happened. G says, I'm going left. P said, I'm going to be G's new boss. After everything is done, we have that true. Look, I am G's new boss, and I went left. Okay. And then you had to deal with this middle piece that got transferred from P to G. Okay. So we can think of it another way if you like. If you don't like this other version, I'm just going to show you a different way of conceptualizing the process. We can think of it as temporarily merging G and P. They come together. So we rotate left G together. So we temporarily merge them together, just like you do with a 2-3 tree. And then we split them back apart. So if you'd like, that's another way to conceptually think. Okay. All right. So I'll let you try. So think here for a moment. If I try to rotate P to the right, what will the tree look like? Try and see it in your head. It's hard to do. If you have paper, give it a shot. And this is going to be the opposite rotation. We're rotating P to the right. So this is X, and X should be as described. Again? Wow. Okay.
I have the recording for each meeting.
Mhm.
I can stop.
Sounds great. Okay. So what's the solution? What might it look like? If I think about it in terms of that little like temporary merge process, that's one way to do it. G and P, let's see, sorry, G. Yeah, G and P, here they are, they get temporarily merged together. Then G ends up being the new boss of P, and we switch back K to being below P. All right. Hopefully it makes enough sense that you feel comfortable enough to proceed. Okay. All right. So let's talk about tree balancing. I want you to give me a sequence of rotation operations that will balance the tree shown here. So what do you think you might do? Okay, just use your intuition. I'll give you like 40 seconds or so. Good luck. Okay, I'm going to spoil this one. So one thing we can do is rotate 3 to the right. So if we rotate 3 to the right, its left child is now its parent. That's the idea. So 3 comes down and 2 is its new parent. And then we can rotate 1 to the left, meaning 2 is its new parent. There's other correct answers as well, but that's one way to do it. Okay. So again, oh yeah. Can we do it the other way around? Rotate left on 1. Yeah, what would it mean to rotate left on 1? So right would be its new parent. Okay. Left, rotate left 1. And then what's the other operation you want? Same 2, but switched. I think about it. I feel like I need a piece of paper to do it. I'm too dumb. What's that? Feels like it works?
Yeah, there's probably multiple sequences.
No, there are definitely multiple sequences. It's not obvious to me unless I have a piece of paper. And because I'm so keyed in on the lecture timing, I'm going to pause on that. I really should be able to do it in my head right now, but coming in too cold, too busy. All right.
I think it's right.
I think it's right too, but I'm a little afraid to say yes, but I think so. Okay. So rotation in general, it can shorten or it can lengthen a tree. And by shorten, I mean you reduce the height, and lengthen means you make it taller. But what's critical is that it preserves the search tree property. It's still a search tree when you're done. Another way to think about it is this diagram here, where imagine I have the letter D, the letter B, and here I have everything between B and D, everything greater than D, everything less than B. When I do rotate D to the right, what happens is D goes to the right and B, its left child, becomes its new parent. So this is the new structure. And then if I rotate left, I go back to the other tree. And so yes, there's a rich set of operations here. If you get comfortable with it, then you could be better than I was here and immediately see, yes, it also works the other way. Yeah.
In this case, the rotate right and rotate back are not as intuitive as flipping, like swapping the two nodes, right? Because you have to look at how the children,
Right. It's not as intuitive as just swapping them. Right. Things happen other than just the labels changing. Right. Yeah. Oh, right. So the difference here is that now I have these children down here. Right. That's the way it feels different. Yeah.
Talking about that, you care about the paper high. Like on one side we have like a very tall tree, but the other side we have like a tree that has one album.
Right. So in the case, the question was, do we care about weight, height? I would say that what you want is a tree with the minimum average depth. That's probably what you want. Yeah. Yeah. So using rotation, we can balance a binary search tree. And in particular, rotation allows us to balance a tree as much as possible in big O and moves. We know that from that thing I said earlier, where you can get to any other configuration in 2n minus 6 operations. Here's a little demo of an ugly tree, and I'm going to do some rotations that when I'm fresh, which I'm not right now, feels intuitive to me. But even me, who's taught this class, like, I don't know, this lecture probably 12 times, because I've been coming in relatively cold, having not thought about a tree rotation in almost a year and a half, for me, I'm going to trust the demo a little, and I'll feel pretty good about it. But I'll tell you that even I, as an expert, it's not obvious to me as I do this probably. Okay, here we go. So a first way I could do this, one thing I could do first is rotate 9 to the left, and you can try and predict what's going to happen. That's comfortable to me. It's not obvious to me that's the right first move, but you could rotate this left. And if you do that, its right child will be its new parent, and we get something that's a little more balanced looking. Okay. Next, we might rotate 6 to the left, meaning who will be 6's new parent? 8. That's the most important thing I want you to understand about rotation. If you can say 8, then great. Okay, so now that's the result of the rotate. Okay, next we might rotate 1 to the left. That means I now have this shape. And then what do you think the next rotation might be? 6 feels good. Right, okay, rotate 6 to the right. That felt right to me too. And we've reached a balanced tree. Okay, so that sequence of 4 rotation operation gets you a balanced tree. So how do I know the right sequence of rotation operations? Well, we could get good at this and have some intuition, or we can use the technique we're about to use, which is to take inspiration from the 2-3 tree. We're going to use the 2-3 tree to model which rotations we want in a binary search tree. It's a kind of mind-blowing idea, but it's very pretty. Okay. So the bottom line is that we can shorten or lengthen a tree, as we just saw, using rotation. We do the reverse operations here. We'll get back to this long tree. And so we just need to find the right rotations. So what does this have to do with 2-3 trees? How is rotation related? I'm going to introduce a new idea. Okay? So first, I'm going to say there's many different types of search trees out there. There's binary search trees, which you can balance using rotation, but we don't have an algorithm for it. And other classes may teach other algorithms, like there's something called an AVL tree that we won't cover. Okay? There's 2-3 trees, which is a different type of search tree. They're balanced by construction. You don't need to rotate. The add operation is such that, and the deletion operation are such that as you make changes to the tree, it always has balance. So what we're going to do is something very clever, but very strange, which is to try and build a binary search tree that is structurally identical to a 2-3 tree. Now, on its face, that may seem impossible, right? Because binary search trees never have 3 items inside each node. Nonetheless, we're going to mimic that process. Seems impossible, but we'll see a way to do it, okay? Now, since 2-3 trees are balanced, if our binary search tree maps exactly to a 2-3 tree, which is just a binary search tree where you allow 2 items each node, then our binary search trees, these new ones, these ones that are mimicking the 2-3 trees will work, or they'll be balanced, I should say. Okay. So I'll start with the most trivial case. If you only have 2 nodes, what's a 2 node? A node with what? Not 2 items. 1 item. Why is it called a 2 node? Because it can have 2 children. Okay. So I hate the terminology, but whatever. So if you only have 2 nodes, which is a node with 1 item, then the binary search tree is exactly the same. That's fine. But what about 3 nodes? how am I going to represent this with a binary search tree? What could I do? Sort of a weird thing. Okay. Well, one possibility is I'll just create like a virtual node. You've done a lot of homework too, hopefully. And you have this notion that, well, I mean, I'm just going to throw in this link or this node that has nothing in it. And all it exists to do is to bind D and F together. So this right here, you can think of it as a supernode, or if you've done like physics, like a Gaussian surface that from outside looks like just DF. And you'll notice that I have B, E, and G down here, but then I have this funky link below that doesn't get used. So the result isn't elegant, and the code's still going to be ugly. But hopefully you agree that this would work. I mean, this is just a normal binary search tree that mimics a 2-3 tree. It just has some nodes which have dummy values. We could just put 65 in there or whatever. Null. Okay, any questions about this? Yeah. Why can't we put E below D? I mean, we could have. I guess that would be an alternate approach. Yeah, we could have put E below D and left the F link hanging as well. That would have been fine. Yeah, so I arbitrarily. Other questions about that? So this is a binary search tree that mimics a 2-3 tree, but it's not as nice as what we're about to do. Okay. So I don't like this wasted link. So I'm going to do what Bob Sedgwick came up with in the 1970s, which is the red-black tree. So what we're going to do is we're going to color our links in our binary search tree. Okay, what does that even mean? Color the links? Yes, we're going to do it. And it doesn't change anything about the tree, like how you read it. It's still just a binary search tree, but some of the links are red. And what's special about those is that red link means these two are really glued together. They're this is now not a 2 node, it's a 3 node. Okay. Now, is this like it almost feels like just silly. Like, okay, I get it. This matches the 2-3 tree, and all you did is make it red. Yes, that's exactly what I've done. Okay. And this idea is actually used in practice. So like the java.util.treeset does exactly this. It thinks about some of the lines as colored. Okay. And so for convenience, I'm going to mark all the glue links as red and also bold them in case you can't see the color red. Hopefully the contrast is good enough with thickness, and we will be off to the races. Any questions about this? It's just a representation. Well, so it seems, I mean, it matches, like you agreed that they match, right? Okay, and so let's explore that matching thing, and then we'll see how it plays into rotation later, okay? So let me tell you a little bit about things. So a binary search tree with left glue links or red links that represents a 2-3 tree is sometimes called a left-leaning red-black binary search tree. So I'm only going to allow these red links to be on the left. They'll never be allowed to be right red links because it simplifies the code. Java util tree set allows red on both sides, but it's easier if you only allow the left. So it's not as efficient. So these trees, these left-leaning red-black trees, LLRBs, they're normal binary search trees. They work like a binary search tree. They just have some red in them, but if you want to find something, you don't care about the color. You ignore it. The only thing that will happen is when we add things, we're going to be paying attention to the colors. Okay? Now, there's a 1-to-1 correspondence between an LLRB and its equivalent 2-3 tree. It's 1-to-1. And that red, I'll say, is just a convenient fiction. The red links don't do anything special for the purposes of finding items. So here, if we think about it this way, this is a 2-3 tree. This is straight out of the Princeton book. And what we do is we add these red links between, but to emphasize that this really is a binary search tree, I don't want these like horizontal lines. Like horizontal is kind of confusing. So instead, I'm going to have this down here. So it's just a normal binary search tree. So realize these two are exactly the same. So what I'd like you to do is think about what would the LLRB look like for this here. Draw it if you have paper. If you don't, then don't. Webcast viewers, you can do it on paper. So the red links only go on the left. All right, I'm going to show you the answer. Who should be the root of the tree? The binary search tree. What letter? W. And who will W's left child be? U. And what color will the link between them be? Red. How many total red lines will there be in the tree? 3, because there's 3 nodes that are 3 nodes. There you go. Okay, that's the tree. And that's the only one. It's 1 to 1. Okay, great. All right. I heard it too. All right. Yeah. It's not balanced, no, but it's close to balanced. And we'll come to that in a bit. Yeah. You can't put U on top because then to glue U and W together, you need a red right link. We don't allow red right links. Other questions? This is the most important slide of the day. Why are red links always to the left? It gives you one less degree of freedom in your implementation and makes it much easier to implement. There'll only be 3 cases instead of 7 cases.
Specifically called left leaning.
Right.
Could have done a right leaning.
Right. Yeah, if you allow both sides, you could have done right leaning instead. That's fine. If you allow both, it can also work. It's just we can't cover it in 50 minutes. Say again? Yeah, only left or only right makes life simpler. Yep.
Let's make it a bit unbalanced, but as it turns out, it's not going to be too bad.
Right. Though I'll come to that later. Now searching an LLRB tree for a key is easy. You treat it exactly like a binary search tree. Where's V? Is WV? No, go left. Is WU? No, go right. V, I found it. So you don't care that the lines are red or black. That'll only count when we add. First question for you. How many of these are valid left-leaning red-black trees? In other words, there exists some 2-3 tree with which they're in one-to-one correspondence. And let me know if the link is asking you for permission again. They start at 3? 3 to 8? Well, how did that happen? Huh? All right. Well, let me fix it. All right, I'm going to reset the options then. 1. That is truly weird.
Maybe you swap the.
No, it's the right question. I see it. Thank you for noticing that. The answers are changing right now. Okay, there we go. It's 1 through 4 now. I guess I should have had 0 in there as well.
Yes, it's not even the right number.
I don't even know the answer too, by the way. Try and figure it out. Bad. 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 I think only one of them. Okay. You heard the answer. This is a good question, me. All right. Okay. Turns out only one of them works. And that might be surprising to you. Let me tell you why they're wrong. So down here is what happens if you translate back to B trees. This right here, this one's not allowed. It has 4 nodes. We don't allow reds on both sides. That just violates our rule. This one, I mean, it seems like it might make sense, but this actually can never happen with a 2-3 tree. You could never get imbalance. It's against the rules. So I agree that there's like an obvious mapping between these two, but this would be an invalid 2-3 tree because there's no sequence of inserts that would ever yield this. You can only have balance in a 2-3 tree. This one is similar. It seems like it should map. And I mean, I would call these two answers like kind of okay, but not that okay. Because it's not possible to actually build these 2-3 trees. And this one can happen just fine. This is a hard question. I like it. Okay. Yeah. This one's invalid because there's no way to get that 2-3 tree. There's no red link, I agree, but this is not, there does not exist a 2-3 tree that matches this. Because this is not a valid 2-3 tree. Yeah. This is a hard question. Yeah. In a 2-3 tree, you could not have 3 values in a node, but in a 2-3-4 tree, you can. So sorry. Curses to the person who made that term up. Yeah. I'm going to pause that. It's a kind of a second order question, so I don't want to take it in the whole room. All right, next question. How tall is the corresponding LLRB for this 2-3 tree? So the height is the number of links to the leaves from the root. And if you're not sure where to start, just think, what's the longest path in the LLRB? Are the numbers correct this time? They're not like 3 through 8.
Maybe this one was 3 to 8. This one will definitely work.
Makes
as 3
sense.
to 8,
Yeah.
Yeah.
Hopefully it's not 1 to 4.
Yeah, this one would definitely be.
No, that's what it was. You're right.
Yeah.
Somehow the answers got copied over. Okay, I'm spoiling this one too. Okay, this one's 5. You might have picked a slightly different number. Maybe you said 6. You were basically right. But I'm counting the links, not the number of nodes. So L to P to U to S to R to Q. Okay. So here's the part where I'm not going to be CS70 on you, and I'm going to say, observe that an LLRB has a height that is no more than 2 times the height of its 2-3 tree. The worst possible situation is that you have a line of pink nodes. So if you have a 2-3 tree, its corresponding LLRB will be no more than twice the height. It should be logarithmic as a result. Okay. All right. Let's talk about insertion now. So what about rotations? How do we connect these two ideas? This is the hardest gauntlet of things in this class, I think, to understand what I'm about to tell you. So good luck. All right. So last important question is, where do these come from? How do you get an LLRB? I understand there exists some one-to-one correspondence, but how do you get from them in a smooth way? Like, it wouldn't make sense to first build the 2-3 tree and then convert it, because the whole point is to avoid building a 2-3 tree in the first place. And why? Because at the beginning of the lecture, I said they're hard to implement in code. Okay. So what we're going to do is we're going to implement insert just like a normal binary search tree, but then we're going to do some rotations after the inserts to match or to maintain the isometry with this with the 2-3 tree. So we'll show that because there exists this one-to-one mapping, we're basically going to use rotations to make sure we're always matching exactly what's going on. Okay. So when I do an LLRB operation over here, I'm going to pretend like I'm a 2-3 tree. Let's do some examples. Let's start with the first thing. I have S, that's my tree, and I'm going to insert E, and I have 2 choices. I can either put E below S to the left with a red link or a black link. Okay, that's the LLRB world, and we want to pretend like we're doing a 2-3 tree. What should we do? Which choice makes more sense? Red, right, because we want to pretend to be an LLRB. Okay, great. So we use red, so we're always going to add with red links. That's the first thing. Design task 2. Let's say we add something to the right. So the tree we're starting with is ABE. And that's also true in 2-3 world. So this is world, the 2-3 tree world, and this is the LLRB world. They're the same. If I add S, we have E and then S. And then over here we have ES. You guys agree with that? That's what we just derived. We should use a red link. But we have a problem here. What's the problem? It's right leaning. Okay. So what could we possibly do? What operation can we use to fix this issue? Rotation. What should we rotate? E to the left. Okay, so we're going to rotate E to the left. And we'll get this rotation. Oh, I gave it away already. But this right here, this is the correct representation. Both of these might seem like okay representations, but we forbade this one. We can't have right links. It has to be left. So hopefully you agree that these two things are the same. Okay, so let's rotate left. Questions so far? That's one of our 3 cases. We're doing pretty good. Maybe that's 2 of them. Okay, let's do a slightly harder one. Okay, first, before I do this, I'm going to give you a new rule. In 2-3 trees, we allowed temporary 4 nodes. Remember, we had those dolmas. It's overstuffed. And then what happens with this S? Splits and moves up. So we're going to have an internal representation where we're going to have temporary nodes. Just like before, where we allow a temporary 4 node, we're going to allow temporary 4 nodes that look like this. And I'm always going to represent these temporary nodes as a left red and a right red. Okay, so it's like a special case just for this situation. All right. This is only temporary, but that's what we're going to do. Okay, so keep that in mind. When I add Z, this is representing ESC. So notice again, we already know how to do this in the last lecture. Here we're adding this red link. Okay, so this will temporarily violate the no right red links rule. All right. Any questions about this? This is the thing I'm going to allow for now. Okay. All right. So design task 3, let's say we have a double insertion on the left. So what I mean by that is I had A, B, S, Z with a 2-3 tree. If I add E, where does it go? It goes into this bottom node. And this is the first stage whenever you're doing a 2-3 tree stuff, right? You allow this temporary node. This right here, though, you'll notice what's wrong here. Yeah. I have 2 reds. Yeah. Well, how are we supposed to represent nodes like this with 3 items in them? It should look like this, right? So the issue is we're expecting like a, but instead we have like a. So how do I get, what should we do? Rotate something. Okay, what should we rotate? This is that first problem we did basically again. So this right here, what rotation operation gets us here? Z to the right. Yeah, okay, that seems right. Yeah, so we'll rotate Z to the right. Okay. All right. So when we insert an E below this S, we need to rotate to the right because we want to match the 2-3 tree. We trust 2-3 trees, even if they have temporary 4 nodes. Here we've done rotate right Z. Okay. All right. So we're doing pretty good here. And then we have one last thing I think we need to think about. I think this is the last one. Okay. This is a really cool puzzle. Okay. So let's suppose we have this LLRB, which includes a temporary 4 node, right? What usually happens is we take the middle item and we bring it up. So we split this node and bring the B up. Okay, you want to ask yourself, what would 2-3 tree do whenever you figure out what goes here? How do we do that? This is okay, I'm gonna give you like a full minute to think about this. So my hint is think about what's the corresponding LLRB and how would you get from this thing on the left to your mental picture? Okay. Thoughts? What can we do? Yeah. Yeah, make these red and these black. So it's not a rotation this time, right? What do? We did like a color flip. So the idea is we're just going to flip all the edges touching B. Okay. The idea here is that we didn't have to rotate at all. In this case, the binary search tree, the magic was inside of it all along. So this doesn't change the binary structure or shape. It just changes the bookkeeping information that maintains the isometry with our 2-3 tree. And so good news, that's it. We just invented the red-black binary search tree. Here's all the rules we derive. When you're inserting, you use a red link. You need to glue it. That's the rule. If there's a right-leaning 3 node, then we have a left-leaning violation. We need to be leaning left, so we'll do a rotate left. If there's 2 consecutive left links, then we have an incorrect 4 node violation. It's supposed to look like this, but we look like that. So we do just a single rotate right, and then we're good. And if there's any nodes with 2 red children, then that means that we have a temporary 4 node. And the way to fix that is color flip. So with just 3 if statements, you can take a binary search tree and you can make it perfectly balanced. You also have to write the rotate operations, but it's actually a minimal amount of extra code to get a binary search tree to be balanced. Though the mental, like the conceptual idea behind it is quite sophisticated. Okay. Now there's one last detail, which is like, this is the base case, I guess, of the whole operation. We also need to think a little bit about cascading operations, which is that sometimes when you do a rotation or a flip, you get new violations that need fixing. So for example, consider the following. When I do that we have this original structure, if you add the letter Z here, only look at the 2-3 right now, please. When you add Z, Z appears in this bottom node, and then we split and bring the S up. That's what happens down below. Okay, we try to emulate that with our left-leaning red-black tree. We add the Z, gets glued in, and then we do a color flip. And here we're pretty close, but you'll notice there's a violation. Just doing this flip left us with what? A right-leaning tree. So what we need to do is fix this so that BS, what should be the new root? S. Okay, so how do you think we do that? Rotate B to the left. Yeah. And if you do that now, you have the correct tree. Okay. But it's just the same set of steps. Like if you see a violation in the tree, fix it using the appropriate either rotate or color flip. So if you have a change at the bottom, it's possible you have to cascade all the way up. That happened with 2-3 trees as well. Sometimes you had a split, which caused a split, which caused a split. Here, sometimes you have operations that cascade up. You don't have a cascade in the corresponding 2-3 tree. But at the end of the operation, there should be a 1-to-1 match. Any questions about this? And so I hope that resonated with your soul, perhaps a little shakily, but that's the core idea behind the red-black tree, which is a famously challenging idea. Now, if you look at the actual Java util tree set, it allows red and left red and right red links. And the advantage is that the resulting code is faster. In fact, significantly faster. But you have to now, instead of coming up with the 4 cases we did, you have to come up with 7. It's really not that bad. It's just tedious. And so if you wanted, you could do it. There's a paper called Left-Leaning Red-Black Trees Considered Harmful, where someone lays out this case that no one should learn this because it's bad, because it's not as fast as the other version. However, I disagree. I feel like it's great pedagogically. And yes, if you need an industrial red-black tree, do the other thing. Okay. I have an optional exercise I'm going to put out there that I recommend doing later, which is to gain some intuitive understanding. I think this is very nice. To try inserting 7, 6, 5, 4, 3, 2, 1 into an initially empty LLRB, and you'll find you get a perfectly balanced BST. I have a little video walkthrough of this, and you can also check through your work later. But I think it's a nice thing because it feels almost too good to be true. But for me, at least, I don't know, something about just manipulating the numbers and drawing it out, it feels good. And this will also give you a chance just to think like, okay, what's the right rotate operation? What's the right color flip? And so you can watch me do it or use this demo. Okay. Yeah. Well, okay. When you're making it in lecture, when you're inventing the idea, of a LLRB. You have to build the corresponding 2-3 tree, but in code, you don't need to. So instead, when in code, basically, you just need to have these rules. Yeah. So we use the 2-3 tree to derive the rules, but we don't need to actually build the 2-3 in general. I'll show the code in just a sec. Okay. So the runtime analysis for LLRBs is simple if you trust the 2-3 tree runtime. An LLRB tree has a height that's log n. We just know that it's always balanced. Or say, we know that a 2-3 tree is always balanced. Since an LLRB is no more than twice as tall as its 2-3 cousin, it's also log n. Contains is going to be trivially log n because it's just it's just a binary search tree. If the height's log n, then the runtime for contains is log n. And then insert is log n. Why is it log n? Well, you have to do log n in the worst case to get to where you need to put the item. And in the worst case, you have to do log n rotation and color flip operations, just sort of climbing up the tree up to the root. We won't talk about the LLRB delete operation. It's not so bad. I have some extra slides that show, only for the 2-3 tree, the Princeton Algorithms textbook, which is where I got this original treatment, which I like more than the AVL tree because I feel like it's a richer topic. It does also cover delete, but actually they also gloss over it because we want to get the idea across without having to go all the way to the bottom of the implementation. But if you'd like, you can write the delete. I've had maybe like 2 people ever come to office hours and have done that, but maybe you'd like to. All right. Did I show the code? No. Oh, I didn't show it. That's a bummer. Okay. And I'm not going to dig it up right now. All right. So I'm going to summarize here what we know about search trees. Actually, no. Any questions before we continue? Yeah. We'll talk about different types of traversals, in order, pre-order, post-order, all that a little later. Do we have the code here? Okay, red, black, BST. I think it might be in the lab, actually. Okay, this is what the code looks like, by the way, for LLRB, since I mentioned it's not much. So in the insert code, this is the usual style of code that you will write for the lab, somewhat different. And the only thing you need to add in order to make it a balanced tree are these rules. So these are the 3 different rules that we derived. You can ignore the size thing. That has to do with something else they like to do with trees in the Princeton implementation. But these 3 things right here, those are the 3 cases we figured out. Like if you look like, so if you look like this, then make sure you look like this. But this is basically you have a right-leaning violation. This is that you have the wrong 4-node violation. And this is we need to do a color flip. And that's it, just these 3 lines. It's very deep though. And I love it, and it's great. Anybody here ever learn an AVL tree? Yeah? Well, how do you compare? Which one do you like better? That one's easier to understand. Yeah. But this one's faster and cooler. All right. All right, let me summarize them. So in the last 3 lectures, I'm now wrapping up trees. So we talked about using search trees to implement sets and maps. Binary search trees are simple, but they're subject to imbalance, right? We know that can happen. B trees, by contrast, are balanced, but they're painful to implement, and they're relatively slow if you want to use them for the type of operations we use them for. By contrast, LLRB insertion is simple to implement. It's just 3 extra lines, though delete is hard. And it works by maintaining this mathematical 1-to-1 relationship with a 2-3 tree. Java's tree map is a red-black tree. You can go look at the code. But instead of maintaining a correspondence with a 2-3 tree, it maintains a correspondence with a 2-3-4 tree. Okay, so it's another higher L. It's the next L up. And it's not a 1-to-1 correspondence. Turns out there's multiple representations if you allow left and right links. Kind of makes sense. So it allows glue links on either side, basically. So it's a more complex implementation, but it is, I am told, significantly faster, though I haven't looked into it carefully. Now, I should note there's lots of other search trees out there. So there's AVL trees, which are probably the most common to teach in a college setting because they're a simple idea. You can learn that one in maybe, I don't know, 10 minutes, the core idea. But there's other weird ideas like splay trees, treats, and so forth. And for every person who was a PhD student at some point in the 70s, people were writing theses about these things. There's lots and lots of different versions. I should note that beyond sets beyond search trees, there's other ways to do sets and maps. One we saw, which was a skip list. That's a linked list with extra express lanes. And then there's also hashing, which Justin will be talking about on Friday. All right, see you, everybody. That's that. How's the Cool. All right.